have Masha Gordina from University of Connecticut. We'll talk about, I thought, Keith kernels and infinite dimensional curved spaces, but there'll be some remaining geometries.
Okay, thank you. So yeah, I'm not Moon, but I'm living in very infinite dimensional world. So mostly I'll do some examples and I'll start with something finite dimensional. I don't know, can you see what is on this slide more or less? So start with some of the ideas where some of the analysis that I was interested in came from. And it came from this picture which describes state space, phase space of some system, and usually people think about n-harmonic oscillators here. And so now I'm going to describe all these spaces and why this picture is better than just this L2 here. So the typical thing is to take your state space as L2 and Rn with the Lebesgue measure. Then what you can do, you can take what's called ground state. So in this case, it's just the square root of the Gaussian. You can find it. And change this L2 to this new L2. And in this case, this transformation is very simple. You just take an L2 function divided by the square root of this density, and you, of course, get an L2 function with respect to this new measure. And it happens to be the Gaussian measure.
So phi is that e to the minus x squared?
It's the square root of, it should have been just this thing with 2 here.
Okay.
Okay. Just square root of the Gaussian density, more or less.
But phi is rho?
No, it's the square root of it.
Oh, phi squared is rho.
So,
And rho is, yeah.
so you take this squared, and if this squared is the same as rho, t, x, they cancel out, and we get the same L2 as before.
And that's what? That's equal to what? That expression you wrote down?
It's the same as L2 just on the flats, on the Lebesgue measure.
Is that a definition or equation?
It's a definition of phi in terms of rho.
Yeah, I'm explaining why it's the transformation is very simple. So if I have a function from L2 on Rn dx, I make this transformation so that phi squared is the same as this rho here. Okay, it's just an identity, and I do get function, new function for this ground state transformation that is an L2 with respect to the Gauss measure now. Okay. So this space is isomorphic to holomorphic L2, and also can be described as what's called a bosonic Fock space. And here we have all the definitions. So this is just L2, this is holomorphic functions which are square integrable with respect to this Gaussian measure here. And these are symmetric tensors, and symmetry comes from the fact that we have bosonic Fock space. So you have these particles, and the H, which you can take as L2 on 0, 1, for example, is a state space of just one particle, or Cm, whatever you want.
Can I ask you, does L2 mean real valued functions or complex valued?
Here they're real valued, here they're complex valued. The point here is actually that these are real holomorphic functions. They're smooth, which happen to be in L2. And these are real L2 functions.
The upper line is real functions.
Real valued functions here. Okay? So
what's the map ST?
I'm sorry?
The map S sub t?
I was actually going to give you a precise description of it on the next slide, if it's okay.
Sure.
Can we go there? Okay. So in this case, actually these 3 maps, so S sub t, some people call it S transform, sometimes it's called Siegel-Bergman transform in this order. So in this case, you can describe explicitly by taking Hermite polynomials in all variables and mapping it to holomorphic monomials of the same degrees. Okay. So and all other maps are completely clear what they are because you just take a basis and you map it to the corresponding basis of tensors L2 and holomorphic L2. Okay?
You just start going from real polynomials with real coefficients to complex polynomials with real coefficients.
Yeah, more or less, yeah.
It should be over complex numbers.
Over complex numbers, so
Everything is
that's,
over the complex numbers, should be then just over C.
this is over C, this is over R.
Right, but you can extend it over C as well.
Yeah.
But it's
No. The map goes from real, I mean, it's formulas, but it's just
Yeah, it's
real
a real
polynomial
map.
goes to the same polynomial with complex variables replacing the real variables.
No.
No.
Same X. Then X and X, they're the same. Like
No, X becomes Z.
Z, yeah. X,
X is a real
This is a-
variable.
But
Hermite
it's not,
polynomial.
it's not just complexifying
X is a real
polynomial.
variable.
You
X
take
is
the
real, but Z is
Hermite
complex.
polynomial of degree K1, you map it to Z to the K1.
thank you.
Just
Yeah.
number of particles, yeah, just the usual.
So this is a Hermite
No, you take a
polynomial.
polynomial and a bunch of variables, and you just think of those variables as complex variables.
that's
No,
Call
no,
them Z.
no,
That's not
no.
what it matters.
I don't know what it
The
means.
whole polynomial is
H.
mapped to a variable. With the right formula, yeah.
What?
The whole polynomial,
Oh, the whole polynomial
Mapped
has
to a
one
variable.
variable.
Yes.
Ah.
Okay.
Absolutely.
So the product of Hermite polynomials like this is total in L2, okay? Real L2. And then you take each Hermite polynomial and map it to the corresponding complex monomial. That's it.
Now, what about this, the
It's
ground
not-
field? The ground field was R before.
Oh, we forgot about it now because we're only looking at this three things
but they are
here.
basis in the complex.
No, but that vertical line goes from real vector space to a complex vector
Yes,
space.
by taking products of
Yeah.
Hermite polynomials to products of complex
What about the
monomials.
scalars?
Others,
But we don't claim that it's an isomorphism yet.
Yeah.
We just say that there is a map from real space to complex
and then
space.
you can extend it to isomorphism. Yeah, there is something to be proved because you have to.
You mean, you can't, after you complexify, you mean, or what?
Complexify what?
Well, Dennis's problem is your first vector space is a real vector space, your second one is a complex vector space.
So this is a map of real vector
No,
space.
so the L2 and Rn should be a complex over C. Just Hermite
no,
polynomials.
I'm not gonna-
Dennis,
I'm not
Hermite
gonna-
polynomials are real valued polynomials, but they are complete in real vector space and they are complete in a complex vector space
No, I know
by the
that.
same. And that's
Yeah,
what shows on
yeah.
the
I know that the analysis is going to work out. I just want to know,
It's what-
I think that's an isomorphism of real vector spaces.
No.
Okay,
Well, I mean, you're not explaining it to me. Come on, I know undergraduate math, and I'm asking undergraduate math questions. What's the answer?
Does it introduce some complex structures that don't
so you can think of this as a Cn as a complexification of Rn, okay? And then you have this isomorphism of Hilbert spaces. Can we move?
No, but isomorphism over R,
Over C.
over
Over
C.
C,
So what is
yeah.
then what is the C structure?
Okay, now I got it.
Of the upper space.
L2 over Rn, you can consider complex valued functions.
So it is complex space.
Okay.
Just consider complex valued functions.
My question makes
Rn.
sense in the finite dimensional piece. And I'm not getting an answer. You just take it out to a certain range, and you're going to get this isomorphism, linear isomorphism kind of. Here you have real coefficients, and here, do I want
So-
complex or not?
So if I understand correctly, the statement is that this is an isomorphism of complexification of the top line with the bottom line.
Yeah.
Well, that's a possible statement.
Yeah.
Okay, the answer is
Okay,
yes.
yes,
Okay, fine.
okay.
So
Now,
the top thing, tensor C, is isomorphic with the bottom thing.
okay, so this is called the Siegel-Bargmann transform, from going from H holomorphic L2 to the Fock space. As we'll see, we can interpret it as just taking this smooth function and taking its Taylor coefficients and getting some element here. Okay, so why anyone would be interested in this picture instead of looking at the state spaces? Because originally, I think Glenn Gross wanted to take n going to infinity. And then this space doesn't make any sense anymore because we don't know what the Lebesgue measure is. But we might be able to make sense of the Gaussian measure here, okay? So we can forget about the ground state transformation and just look at this thing here. So what I'm going to do is eventually, I want to look at a similar picture where I replace Cn by something curved and infinite dimensional. Okay, and you might ask me at some point why I'm not doing L2, and I'll tell you later. Okay, but right now I don't want to concentrate on that. So first, let's look at what happens in just infinite dimensional linear case because it's a good test on what we can expect, what kind of complications we'll see. So what I want to do, I want to have an analog of the Gaussian measure, and the reasonable choice in this case is what's called an abstract linear space, but we can think of just W being complex valued continuous functions with the subnorm on, say, 0, 1, okay? H being Hilbert space of functions whose first derivative is an L2, it's a Hilbert space. Different norms, right? This completely different norms. And then Gaussian measure is defined by its Fourier transform here. Okay? It's known to exist. And the interesting part here is that, as you can see, the right-hand side here is determined by the norm of this phi essentially in this space of this Hilbert space. Okay.
And what star means? You write H, Cm star.
Oh, these are
star.
duals.
No, in the norm. No, in the norm. Dual space itself in exponents.
I should have not put it here, but essentially you interpret phi as an element from the dual of this W and then evaluate this norm. Okay, you cannot really write the Cameron-Martin norm here, but essentially it's determined by the Cameron-Martin.
Hilbert space.
Yes.
It's a triple.
Yeah.
It's
Yeah.
triple.
No, because W is a bound space, and in his picture you have 3 Hilbert spaces. Okay. So what happens here is once you define this measure, the original. So usually you start with Hilbert space like this, and then you construct Gaussian measure there, you complete it so that you get a nice measure, and actually you end up in W, and the original space becomes a set of measure 0. Something that doesn't happen in finite dimensions. So it's a very, yes?
Okay, so if you have any separable Hilbert space density embedded in a complex separable Bonnet space, you can make this construction.
Yes.
And it'll be abstractly isomorphic to this one if the Hilbert spaces, the Bonnet spaces, abstractly isomorphic.
Yes.
Okay.
So that's what's called an abstract linear space. But if
And
you
the
want
measure
to
will live out in the full space and not
Yeah.
on the Hilbert space.
Yes, exactly. And here's, you probably cannot really see what's written here, so there is what Glenn Gross wrote about Urban Siegel, and somewhere in the middle here, he explains this phenomenon of trying to construct a measure on this Hilbert space and ending up in this huge space W. And as he says here, that it's actually, if you think about it, it's very similar to how you construct Lebesgue measure. You start with rational numbers, right? You complete it and you get the whole interval, for example, right? And the original set becomes a set of measure 0. But there are some other things that do not go as they do in the one-dimensional case. And here in this paper, also Leonard Gross said that actually Siegel always said that all the analysis on this W space is controlled by this very, very small space H. So it has measure zero, but if you want to differentiate functions or do any kind of analysis, there you have to go back to this stage. Okay? So that's an infinite dimensional phenomenon. And now let's look at what happens if I just replace Cn by, say, group or Riemannian manifold. And so that was done by, so this, the holomorphic L2 from complex group to the Fock space. That was done by and Gross. And so what happens? So holomorphic L2 makes sense. Instead of Gaussian measure here, you have the heat kernel measure. The Fock space becomes more complicated because your particle lives actually in Lie algebra, not.
Did you say what HL2 was? Sorry.
It's holomorphic L2, so
Functions, polar functions of the
this is finite
so it happens to be an
dimensional.
L2.
Yeah.
For which measure? The calcium?
Heat kernel, yeah.
Heat kernel, okay.
So in this case, it's just heat kernel times power measure. So that's the fundamental solution to, say, heat equation with Laplace-Beltrami times the power measure for, at least for Lie groups. That's enough for us. Okay. And so actually you can describe this bosonic Fock space in this case as a completion of the universal enveloping algebra, and that explains why, in principle, if you look at this algebraic object, you might be able to recover all the information about your group in some sense.
G is a complex Lie group.
Yes, yes. Because we need holomorphic structure here, so otherwise it doesn't make sense.
What does the arrow mean? Oh, the arrow, the bosonic Fock space are these Hermite polynomials we were talking about before?
So what I'm trying to say here is where the flat thing goes in this non-flat picture. So Cn is replaced by a Lie group, complex Lie group, or Riemannian manifold in principle. The bosonic Fock space is replaced.
Which was what before?
The bosonic Fock space was this symmetric tensors.
Oh, you get from the derivatives?
This.
Oh, no, just this formal thing. Oh,
Okay.
right.
So an algebraic object
Yeah.
at this point. So you can construct a similar thing, but the state space of one particle is Lie algebra here, Lie group here. And so what I will be interested in this infinite dimensional setting, which we're not in yet, is how geometry of, say, G is connected to Brownian motion, heat kernel, and all the spaces. So what we usually know is that, so you might have a complete manifold which is not what's called stochastically complete, which means that there is some loss of heat somewhere. And there is not a good characterization of that, but there are some geometric conditions under which you have stochastic completeness. For example, if you have a complete manifold and you know that the Ricci curvature is bounded from below, you know that it's stochastically complete. There are other conditions which are, so Ricci is the only thing that is probably more applicable in this infinite dimensional settings, and that's why I'm going to talk about it. I'm not going to give you all other conditions that you might have. Okay, so now if you try to do this kind of analysis in some infinite dimensional curved spaces, here's what kind of problems we might have. So first of all, in finite dimensional case, so what you have the proof here, and the Lie algebra is just tangent space. At least that's what we think about it, right? So, well, if you do it in infinite
So that's a
dimensions,
picture of the three-sphere, SU2, is that what you said?
yeah,
Okay,
it's
fine.
just finite dimensional Lie group. So if you're doing this on infinite dimensions, you actually have to make a choice what your tangent space is. So you choose different norms on that, and you change this as a set. You change the topology of this, and the whole picture changes. So that's something that does not happen in finite dimensions. And if we think about how we differentiate functions on, say, big group, what we do, we take an element from the Lie algebra, so that's, we take function and move any element in the group along this exponential, right? And we take the derivative of this. Probably wondering where my probability is. Yeah, it's coming. And you take this derivative in time, and that's what we can think of the derivative of f in the direction from c. So if you change the Lie algebra, as I said here, you might actually change the directions in which you differentiate. And if you take too many directions in which you want your function to be differentiable, you might end up with not too many functions. So it's actually happens. And finally, if we think about heat kernels or the heat equation, well, we can think of the Laplacian as being the sum of second derivatives in the directions from an orthonormal basis, and therefore this choice actually determines the Laplacian and eventually the measure that I'm interested in. So it doesn't matter what you choose, but you have to stick to that and see what changes on the other side of this picture. So also, it's relatively not
Can I, I'm trying to keep up here.
yeah.
The previous discussion when we first started, you replaced your real overspace by this complex, and you talked about holomorphic functions. Is that, now we're talking about curvature and so on, we don't need holomorphic functions. How's that going to help us?
Okay, that's something that I kind of said I don't want to talk about it, but is it okay right here? So we have L2, we have holomorphic L2, and then we have this bulk space here.
Right.
So what happens is that the Siegel-Bartman transform, even in finite dimensions, can only use added variant in a product here. Which means that once you move to infinite dimensions, there is no hope, because we don't even know this in finite dimensions if you can do this, and it's a very subtle analytic problem. So that's why all this infinite dimensional thing is concentrated on this. So you might think it's technicality, but I don't think so.
You're not going to use holomorphic anymore.
Actually, I am only going to use holomorphic.
Huh?
That's the only thing that I will be doing. Holomorphic.
Yes or no?
Only
Only holomorphic. Only holomorphic.
Only holomorphic.
Because this result of driver and cross used not necessarily at k invariant. So if this is a complexification of...
Well, I'm happy if you use holomorphic for something.
Yeah.
You are going to use it?
I'm going to use
good.
only
I'm
holomorphic. Okay. Because that's the only thing that survives.
It's not obvious that holomorphic things can be used. Right.
Yeah,
Yeah.
but you can use them actually. Okay. So I'll talk about this. Then again, in this case, of course, I cannot use something like this because first of all, I have to solve a PDE, which in infinite dimensionals you might not be able to do, and also I don't have a Haar measure.
So you had a chance because there are two things wrong.
Yeah, together in one big thing. Yeah. And eventually, all this business was developed by many people to make sense of what physicists usually use. I don't know if you can see what's written here. So you can see quite often this expression. So what you have here is normalization constant, which is either 0 or infinity. you have this thing, so which makes sense only for our Cameron-Martin paths. And here you have infinite dimensional Lebesgue measures. So you have plenty of things that do not make mathematical sense. What we can do, we can actually make sense of the whole thing, the whole expression, rather than each component here. Okay?
So x here is a function on
It's a
interval.
path, yeah.
It's a path.
So it's a path from interval, in this case, 0t to something, which I did not specify. Usually some finite dimensional group or something. Or maybe even flat space. Okay, so I hope to talk about a couple of different examples and or class of examples rather. So the first one is what I call Hilbert-Schmidt groups, and I kind of stopped doing it, but I'll tell you what I know about it. So there are lots of things written here, but essentially the main examples we should keep in mind here are just infinite matrices. So the space that I'm looking at are invertible operators, bounded linear operators on a complex Hilbert space. Complex because I want to have holomorphic functions eventually. So then this space is kind of nice, except that it doesn't have a nice inner product. So therefore, we consider what's called Hilbert-Schmidt operators here. And essentially, we can think of this as infinite matrices like this. This is an infinite matrix, so that the elements are in little L2. And I think
your space is separable, right? So
Yeah,
separable.
yeah. I didn't say it. Yeah. Okay. Yeah. Is it okay? No. So what I want to do, I want to have a Hilbert manifold in this case, where the my tangent space will be this Hilbert-Schmidt operator. So the tangent space here is this HS. Okay. Unfortunately, things do not work as well as in finite dimensions, because remember what happened with this abstract Wiener space? We had two spaces, W and H. So here what we're going to have, probably, is something like this. You're going to have your kind of W here, right? Then you have smallest space here, like H. And then you take it to your curved space, and you'll probably have two spaces, one corresponding to W and one corresponding to something smaller. Okay? So instead of two objects, you have four. Two flat and two curved. So this G
So like
here.
Leon, I mean, is it borrowing an idea from Leon earlier today? Should you think of this like foliation of the, we have a manifold modeled by W and then,
Okay,
and then the cosets of H?
So when I was
Give your
doing it, I
foliation.
didn't think about it this way, but now I actually do. So I think what happens, and it's not formalized yet, but what happens is that this W, yeah, you can actually, you have lots of copies of H which fill it
The
out.
cosets.
Yeah.
And the nonlinear analog of the foliation.
Yeah.
Okay.
And actually,
Thank you.
I have a completely different example now where you can see it very clearly, and I can write what the distance is and why you have it. But I'm not doing it here yet. Okay, I just have one copy for now. Okay, so this capital GCM is this little thing here. So it's Cameron-Martin. So this large thing is G. So that's not me. So W corresponds to G, and H corresponds to the Cameron-Martin. Okay.
Hello?
So now I want to define some kind of Riemannian structure here, and I'll start from the distance function, and you do the same thing as you do finite dimensional. So you have a path in the group, the infinite dimensional group, and you find this, the infimum, and all paths, and so on. So here, the difference is that in finite dimensionals, no matter what inner product you choose on this G, you're going to have more or less the same distance, okay? Topologically, it's not going to change anything. But in infinite dimensionals, actually, this choice will change, for example, the set on which this distance is finite. So that's a huge difference. And at some point, we'll see that you can describe this Karman-Martin subgroup using this Riemannian distance. So here, I'm just repeating what I was trying to draw on the blackboard. So these are infinite matrices. We have the standard basis of 1 and 2 as everywhere else. So as I said, we usually do not keep our invariant in the product. We scale it. And I'll scale it in such a way that this scale is formed in little L1 sequence. So, for example, this is one of the choices, and that's the choice that I think Malivan used in one of their papers. Okay, so that's just repeating what I said before. Okay. Are we okay? So here are more examples. So you can do the usual, all the usual matrix groups like GL, orthogonal group. You have all your usual suspects here. These are operators, but who cares? And you do have a nice Hilbert structure from the Hilbert-Schmidt operators. And we also have a symplectic group here. Okay. So now, at some point, Marian asked me if I know anything about the Ricci curvature of these groups, because the usual intuition is that if Ricci is bounded from below, then lots of analysis should go through. And so that's not a very pleasant computation, but one can do it. So actually, it's based on Milner's paper in finite dimensionals, where he looked at what happens in finite dimensionals if you change either product on the Lie algebra and how curvatures change. That's exactly what I want to do, just in infinite dimensions. Okay, so he derived formulas for lots of curvatures using only the Lie algebra structure, inner product and Lie bracket. Okay, so that's the idea. And so I say it like this, but essentially.
Who's he? I couldn't hear the name.
Jerk.
Huh?
Jerk.
Thank
Can't
you.
hear that name either.
Jack Milner.
Milner.
Huh?
Jack.
Oh, Jack. Oh, okay.
I didn't say that, but
Okay. Wow. I was 60 before I allowed myself to say that.
okay. So I still have some time to go. Okay. So what happens is that, it's not a mathematically rigorous statement, but essentially, no matter what reasonable scaling you choose, Ricci curvature is not bounded from below. There is nothing you can do about it. So all these techniques that people develop.
At every point, there's.
Yeah, so I actually write what it means here, but I'd rather skip it for now. I just wanted to impress you by all these computations, but it's not very interesting. So essentially, you can write explicitly.
Wait, what about the upper triangular? That one's bounded, isn't it?
Yeah, so I didn't do this. So I only dealt with highly non-commutative things
Okay, fine.
in that paper. Okay, no new important stuff, nothing like this. I was actually interested in orthogonal originally. Okay, so let's go back to this picture for the objects, and this Karman-Martin group can be described as the set of all points to which this distance is finite from the identity from. And So here, what you can prove is, you can prove something about exponential map, which is what I'm going to do. So what's written next is the following idea. So you have this infinite matrices.
And this is a little surprising. You're saying there are points that are an infinite distance apart?
I'm sorry?
There are points that are an infinite distance apart?
Yes.
But it's sort
Most
of,
of them.
Huh?
Most of them.
And there's sort of a connected space too, right? It's connected, right?
Yeah. Just not in this.
Yeah, this is a new phenomenon.
It's welcome to infinite dimensions.
And welcome to reality, okay.
Yeah.
Yeah, I told you I was afraid of the infinite dimensions.
But that's actually coming back to this. I think what happens is that actually you also have just pieces.
Oh, you have to go along the leaf. You have to go along the leaf. Oh, like the kernel geometry.
Yes, exactly.
Ah, okay.
It's exactly the same.
So you take all of this, then you take another point which is not in this set, and do the same thing until you. Okay. But that's not. I didn't know this at that time, but now I know. Okay. So I take this finite dimensional approximations here, and that gives you this inductive type limit for the spaces. And so what I proved was that if the Lie bracket, which is just an arbitrary Lie bracket, I never said this, but that's what I'm using, is that the exponential map is a local diffeomorphism from the Lie algebra that we have to the Cameron-Martin, this small space only. So it's a very natural space in which you, again, will do your analysis. And also, the finite dimensional approximations here, that's a relatively subtle result. And I'm not going to talk about it, but just mention that actually the groups, you can approximate this Cameron-Martin. So that's an alternative description of Cameron-Martin subgroup. Here, it's a real subgroup, by the way. I mean, real, like reality. Okay, it's a subgroup. Okay, so I don't know what was sent to the department, but apparently I was described as a probabilist, right? And we didn't have any probability in the first 40 minutes of this talk, so here we have some probability. So eventually I wanted to construct this heat kernel measure. And this is why you cannot really, I think, you cannot use anything but probability. So what you do, you just take, you use the fact that actually the Gaussian measure and the heat kernel measure, even in finite dimensions, corresponds to stochastic process, and what's called its transition probability is exactly the Gaussian or the heat kernel measure. Okay. So in this case, and this is why I was using this Hilbert structure a lot, is you take your Brownian motion on flat space is just the sum of one-dimensional independent Brownian motion. So this is an orthonormal basis of Lie algebra. And
Can I perform a service in, say, 30 seconds of what a stochastic process is?
well, Brownian motion is okay. So
I wanted to do it. Because I'm not going to do anything mathematical. You're going to say that. The stochastic process is like your life. Every day in the future, you get up in the morning, you have certain choices. Each day you have new choices. You imagine all of the possible lives you have, and you have some probability distribution on what the outcomes are.
okay, thank you. So, and did you want to describe what the Markov process is? That's when you don't remember what happened in the past.
Oh yeah, and every day when you get up, you don't remember the past. You never learn from your mistakes.
Yeah.
Right.
So it's perfect life here. We have a Markov process.
Right, forgot
Thank
that.
you. Yeah. Okay. So we have this process. I don't remember anything that happened before that. And here, again, I'm not going to explain everything here. So it looks like a differential equation, right? If you think about derivatives. Only difference is that this is just a continuous path. It's not differentiable. This is not differentiable. But you can make, some people can make sense of this, right? And it's a stochastic differential equation that we solve in this Hilbert space of Hilbert-Schmidt operators. So you might believe me or not that we can do this. And here, this is multiplication of operators actually. So these are operator valued solution of the stochastic differential equation. So you can actually write what inverse is, and it's a kind of funny thing because you can write a stochastic differential equation for both of these things and then prove that it's the identity. So the left-hand side is random, depends on t. The right-hand side does not depend on anything like this. And we say that it's like this with probability 1 for any time t. And you prove it by using a standard method in stochastic analysis, which is called Ito's lemma. So, which is essentially how you take derivatives of products in this world, in this very strange world. Okay?
So here you're solving for an operator.
Yes.
Okay.
Yeah. Okay, so then, and here's why we don't have to deal with PDEs in infinite dimensions. Because this theory tells us that actually the solution gives us a solution to this equation, which is x, gives us a solution to this parabolic equation, which is written in this form, which is essentially second derivatives here in the direction of the basis, plus some first order terms here. And if you write it in terms of the Lie group that we have, say for the orthogonal group, you just get the usual Laplacian you would get here, the group Laplacian, nothing else. Okay, so what happens is that we don't have to solve this PDE directly. We can use this theory to say that we have a solution, and actually that...
But why did you write two equations? They didn't seem to be interacting very much.
Here.
Oh, that. Oh. That's part of the condition?
No. If you,
these two equations do that.
Yes.
Oh, I see. You
So you solve them
You
and
solve
then-
for the map and its inverse at the same
Yes,
time.
yeah.
Okay,
Yeah,
I see.
you can do it separate and then say actually it happens to be the
Okay.
group inverse of
Okay,
that.
okay.
And you can verify it by differentiating using ether differential.
Yes.
You get extra term which there's
Yeah, which cancels out,
no
yeah.
minus, right?
Yeah,
Otherwise
it's
you
like
get
one
minus.
line.
He likes
It's
to
one line,
calculate.
yeah. It's funny. It's very simple
Yeah.
if you know how to do it. Okay, so that's why we call this measure the heat kernel measure, even though we don't have the heat kernel to speak of, but that's natural if we have that it gives us solution to the heat equation. Okay? So, okay, this?
So this is, instead of the Gaussian measure, this is going to be the measure you produce.
Yeah, so
And what was the
usually,
data? What was the input? You had these coefficient functions, I forgot. What do you have? You have Brownian motion. on
so
the
you
Hilbert
start with
space.
the Brownian motion on the flat space, or
On
Hilbert
the flat
space.
space, and you push
Then
it around.
so it's what's called multiplicative.
Okay.
So it's,
Okay.
okay, if you write GT,
Okay,
if
okay.
you multiply on the right, it's like Cartan development here, so it's the
So
usual.
the trace class operator tells you on the tangent space what the Brownian motion is?
Yeah, so it keeps
The
it in check
variance.
so that it doesn't live in a much larger space on your group that you want it to live it on.
Oh,
So the covariance for W keeps control, because otherwise you would have to live with some non-clear what it is, some kind of monster. Like completion probably, some. Okay. Is it okay if I go to the next? I'll just talk about the next example a little bit. I'm not going to give any details here, but I'll just, so that's a different type of example, and the difference is, there are two main differences here. It's infinite dimensional Heisenberg group, as it was joined work with Gross driver, so it was all published. The difference is that, first of all, in this case, the manifold is not Hilbert anymore. It's actually modeled on Banach space, W. And secondly, actually, Ricci curvature is bounded from below, and you get lots of interesting results here. So in some sense, we have a complete picture here, unlike this Hilbert-Schmidt.
what Banach space can I think of?
Continuous functions on finite, the usual classical.
Okay.
So here is what happens actually. So if you think about typical Heisenberg group of vector space, what you have is you have vector space and you have a symplectic form omega here, which makes it, which gives you this group, right? So it's a group vector space. We can think of this here, W, with omega being the symplectic form, which makes it into this group. So it's the usual addition, right, plus the correction term.
So this could be this space h1/2 on the circle.
Yeah,
And
it
that
can be.
integral of FDG is a symplectic form,
Yes.
right?
So there should be some conditions on, so if you want to do some analysis, there should be some conditions on omega, which I'm not really interested in right now, but eventually we'll go on. Okay? So remember that we have two spaces here, so for each of them we can construct the corresponding group, and that's what we'll call Cameron-Martin subgroup. So it's
And the W becomes the Hilbert space.
W.
You still have the C, okay.
C is the center, yeah. I'm just doing one-dimensional center. You can do finite dimensional center here. I just didn't want to carry all the notation.
So to speak, the Haar measure, or Gaussian Haar measure of H cross C, which is a nice Lie group, lives on this bigger space W.
Yeah,
It
exactly.
doesn't live on the,
It's
Where
not
it's
going to
supposed
live
to.
on this small space, yeah. So in this case, you can actually write what Brownian motion is explicitly, and I have to say that it's a little bit more tricky here, but I'm not going to talk about it because it's a Banach space valued Brownian motion. But we can make sense of this thanks to Langros. So you can write what a Brownian motion is, and since I'm presenting here probability, I can tell you that this term here stochastically is very complicated, surprisingly enough. So that's what's called the stochastic area, and it's still being studied. Okay, so in this case, we construct this heat kernel measure, and it's what's called quasi-invariant under the shift by the Cameron-Martin subgroup only. We can compute the Ricci curvature, which is bounded from below if the symplectic form is bounded as a map from this space to this space. Okay. So then, what you can prove also what's called log-Sobolev inequality. So essentially, once you have the Ricci curvature bounded, you can get this. And we can prove this Taylor isomorphism of holomorphic L2 and Fock space, which I actually did prove for the Hilbert-Schmidt groups as well. I didn't say it, but you can do that, even though you don't have all these nice properties here. Okay, can I just mention this and then I'll finish just. What is 15
maybe an
minutes?
hour talk, I think. Yeah, it's an hour talk, yeah. You have 9 minutes.
Everybody's still kind of
And
alive.
48 minutes and 30 seconds.
Okay, I'll try to. So that's the last example that I have, and it's probably the least satisfying because I don't really have good construction here, and I'll explain why. Okay. So. So the idea here was that it was known that the Ricci curvature is finite here, whatever that means. And so several people tried to construct Brownian motion on these groups or some groups associated to this. So I'll tell you what this amounted to. So I described here what the group, the object is. So we start with smooth orientation preserving diffeomorphisms of the unit circle. It has the Lie algebra here has a very nice structure, so you can describe it by just this vector fields here. And so in this case, as I said, it was known, and I think it was done, the first computation by a physicist of the Ricci curvature. And did I say something about the, I forgot to say what, complex structure. Okay, it's described here. So what happens is that the rigid curvature is finite here, and you can compute it, and we did a somewhat different computation from the previous ones. The problem is that it's finite because you have a scalar structure there, which gives you symmetries, and there are some cancellations that happen. And so it becomes finite, but if you really go back to the real vector space structure, you see that there are lots of infinities there, and that's what prevents you from constructing a good stochastic process. That's what our impression was. So the computation due to this famous constant here, and this is what I explained here, that the rigid tensor for the original derivative without this complex structure actually diverges, which means that if you write the corresponding stochastic differential equation, you have something that doesn't really make sense, and you cannot really solve that unless you scale something. And this is what people try to do with this. So, so I mentioned some of the people who, and I think Tolmeier somehow got excluded from here. I don't know why. So Errol, Marvan.
Oh wait, so when you said the cancellation, does that mean the sectional curvature is actually infinite? Is this trace
No,
that makes
it's
it cancel?
the, if you look at the nabla, actually to do any reasonable stochastic analysis there, you need it to be Hilbert-Schmidt operator, and it's very far from that.
Okay.
So one of the ideas was that, so it was done by these two people. They saw that there is, so they used a picture of Kirillov, I think, this M infinity space, to see that there is some kind of infinite dimensional symplectic group here. And then you can construct Brownian motion on this group by just solving the same kind of stochastic differential equation as before. The problem with this is that actually this group is very far geometrically from the space that you're interested in. So it's a nice construction, just doesn't give you what you want. Actually, what they also did, they introduced the scalars that I mentioned before, and what it does, it really changes not just the group itself, but the geometry of the whole space. So it was not the space that they were interested in, or I was interested in, or most of the people. So there was also work by Marvan and Funk, and I think some other people, but that's more or less that's cool. So essentially what you want to do is you want to get to this metric here, and so what they call the canonical Brownian motion then does not live in that space of diffeomorphisms, but rather in a much larger space of homeomorphisms, which is not surprising if you think about this picture. So you always start with something and you end up with a much larger space. So, and finally, I just want to mention my student here who actually, one of the problems is that on all the spaces you don't have Hilbert space structure, you don't have bounded space structure, but rather a Fouché space structure. So he did construct Brownian motion on the space using some sophisticated approximation by Fouché space by Hilbert spaces. And it's a relatively, it's a complicated construction, but the result, the gain, you lose invariance of the Brownian motion that they actually wanted for the measure. So it's still not completely satisfying, but at least there are lots of different approaches, and that's where the stance is. As I said, I'm not completely happy about this, but that's how it is. I think I'll just stop here. Thank you.
Any further questions or further comments?
Further, why do we further? That's the first question.
That's not a question.
So, when you say you want to show this thing exists, it's not just building the Brownian motion and writing the equation. I mean, you can build the Brownian motion,
Yeah.
always on the Lie algebra sort of. You write the equation, but then
I want it to live right where it should live, not in a much smaller space or in a much larger space. So this
no, but I mean,
eclectic
even
group-
Brownian motion has this property that the measure lives on the bigger space.
Exactly. So there are different approaches to this. You can either choose this larger space to be exactly the space you're interested in, right? Or you can start with that space and end up who knows where. So if you want to end up in the space that you're interested in, you have to choose everything here very carefully, right? So that you don't end up in a much smaller space here, which is what I think happened with the first attempt with this eclectic group.
Is this Brownian motion, as usual, is it the limit of the discrete time random walks or not?
You can describe it like this, but that's not how you construct it usually, yeah. So, I mean, usually, yeah, you have your random walk here, and you take small and small steps, and you get
But
to...
it's still true in this situation, it's still...
I'm actually not completely sure, because you have to specify what the distance is, and that's complicated. So I think on a manifold, on a finite dimensional Riemannian manifold, you can interpret it this way. That's okay. But in infinite dimensions, I would hesitate to say, just because it's. Did you see my point that you have to choose which distance, what is?
But you do have directional probability, so for the one step.
Directional probability.
So if you have discrete motion, so you go in this certain probability.
I think I'm more worried about convergence, right? Because say on a plane, what you do, you take random walk, and you have some kind of convergence of random walk to the Brownian motion. So in which sense we understand it, how do we measure that they're close or far from each other? That's maybe, did I understand your question?
What about Brownian motion just on a flat Hilbert space? Can you do that with an
Yeah,
approximation
that's
by random walk?
not a huge problem, yes. It's like a vector space. It's just an approximation of, finite dimensional approximation of something. It's not, the convergence there is no, everything is fixed in some sense.
And can you use the meshes you constructed for applications to some field, quantum field theories like Euclidean, because you are doing Euclidean version, like sigma models on the curved spaces, probably should be related.
Yeah, so one of these projects, which never was completed, was together with Rajiv and Landros, and I'm not sure that it was exactly Euclidean, but it was about nonlinear sigma models. Yeah.
In Euclidean space time, because you have like a measure, a true measure. Right?
So I don't know to claim anything, but that's definitely somewhere.
This would be very interesting.
So yeah, one of the things that we try to do, and we still are trying, is to get it to connect to the non-linear.
It seems strange to me, though, that you should make this big psychological difference between the tangent space and the manifold. I mean, you have all these nice processes on the Hilbert space slightly extended to this bigger Banach space, right? Mm-hmm. And then you have that at every place in the manifold. Why can't you just lay it down in the manifold and have a process?
How? No, I'm sorry.
Just go like this.
I'm really interested, so.
I mean, for me, there's not that much difference between the manifold and this sort of field of tangent spaces with a little distortion, very small distortion. I mean, everything is down in the manifold.
There is a distance.
Yeah.
So when you write the formulas, you're in trouble because somehow the picture doesn't.
Oh yeah, pictures. But when I look at this picture, I understand, I think, everything. But once
I mean,
you
it
try,
seems like the analytic difficulty has already been absorbed by you have the Cameron Martin Tilbert space, the bigger Banach space. Well, there's the analysis. Done it.
okay, but try to prove, for example, just what the measure of this little thing is. You'll see all this non-linearity coming in. It's not as, because you cannot just look at the local picture, because you're thinking about very local picture, right?
Yeah.
Once you want to have a measure, you cannot just do it like this. There's two
Well, for small
structures.
time, most of the measure is pretty near the origin.
Well, then you have this little piece which has measure 0, which controls all the analysis. That's strange. So your intuition would work really well only on this Cameron-Martin subspace here, Cameron-Martin subgroup here. That's fine.
And it has measure 0, right?
And it has measure 0. So you see that as with the Hilbert-Schmidt groups was what? I have the exponential map as a local diffeomorphism from here to here, to this little thing. And lots of other nice things, but it's only on this. But once you go to polymorphic L2, just to make sense of that, you're in trouble. I didn't say anything about that, but it becomes much more complicated than in finite dimensions.
More questions? Well, thank you very much.